actuation has proven to be the most popular approach to controlling soft robots due to commercial availability of control components, ease of power delivery, and existence of lightweight actuators. However, a significant challenge in pneumatic actuation or fluidic actuation is the scalability of fluidic control systems. The sophistication and complexity of many soft robots critically rely on simultaneous and independent control of multiple actuators. Usually, the control of large array of actuators requires each actuator to be connected to a dedicated electromechanical valve for independent operation. This places a practical challenge in designing soft robots with many actuators. A major challenge with approaches like fluidic demultiplexing presented in the literature is that they are only able to control one actuator at a time, thus increasing the refresh interval proportionally with number of actuators. In this work, we present a fundamentally different approach to independent control of many pneumatic actuators that bridges the trade-off between direct actuation and fluidic demultiplexing. We call this approach fluidic matrix circuit. Our approach is inspired by electronic circuits that drive dot matrix displays, which are controlling large array of large array of LEDs with a high refresh rate and good scalability. As shown here in the image, you can see that although the LED display appears to be on, displaying letters UCSD, an image captured with high-speed camera shows that only a set of LEDs are on at the same time. We take this inspiration from how a dot matrix display works by controlling flow of electricity through each row and corresponding column pair to control every individual LED. To enable this concept, we construct a fluidic logic module, which is an intermediate circuit element that allows actuation and retraction based on the state of the mass flow at the inlet and the outlet. As you can see here, when the mass flow is enabled through inlet and the outlet, it causes retraction due to vacuum generated in the signal line. And when the mass flow is blocked, the positive pressure is generated in the signal line, causing actuation. Arranging this fluidic logic modules in a 2D matrix pattern and connecting all the outlets of these fluidic logic modules together in a row, in a column, and connecting all the inlets of these fluidic logic modules in a row enables us to design and control a fluidic way. To enable this concept, we construct an intermediate circuit element that can generate an actuation signal based on the state of mass flow through the circuit element. We call this circuit element a fluidic logic module. As you can see here, when the mass flow is enabled to inlet and the outlet, it generates vacuum in the signal line, thus causing retraction of the actuator. When the mass flow at the outlet is blocked, but the mass flow at the inlet is still enabled, it generates positive pressure at the signal line, thus causing actuation. When these fluidic logic modules are arranged in a 2D matrix, with all the outputs of these fluidic logic modules connected together in a column, and all the inlets of these fluidic logic modules connected together in a row, the control of mass flow through each fluidic logic module can be enabled and disabled by the corresponding solenoid valves connected to each row and column. Thus, we enable a fluidic matrix circuit capable of independently controlling a large array of actuators using a limited number of electromechanical valves. The array of actuators connected to the fluidic matrix circuit was refreshed sequentially by addressing each row within the matrix for a short period of time. As you can see in this illustration, opening the R3 valve enables mass flow through the inlet for the last row. However, the state of solenoid valve and the outlet for each column determines the state of the actuator. Thus, we can actuate and retract an array of actuators by controlling the mass flow through the corresponding row and column. This video shows the control of an array of actuators using our fluidic matrix circuit. A row of fluidic logic modules connected to one inlet manifold within the fluidic matrix circuit is turned on, and then the specific fluidic logic modules within the row were addressed by switching the states of the electromechanical valves in the corresponding column. Hence, controlling the actuator involves controlling the state of the corresponding row and column, as shown in this video. We demonstrate the implementation of a fluidic matrix circuit for controlling a fluidically driven shape-changing display with 25 independent actuators arranged in a 5x5 matrix. The shape-changing display could render various shape patterns, including geometric patterns, numbers, letters, graphics, and incoming visual data. We demonstrate the shape-changing display, rendering every frame of a snake game as the position of the snake was dynamically updated on a 5x5 grid. The two-dimensional array of actuators was refreshed by sequentially addressing each row within the matrix for a short period of time, as shown here. We also demonstrate the use of 5x5 shape display controlled by a fluidic matrix circuit to generate desired patterns to convey and manipulate objects. The tactors used were used to generate the height profiles to confine the object within a cage and to guide the motion of the object alongside the desired path. We demonstrate the pattern generation for object manipulation to convey the ball along a row, a column, and diagonal of the shape display. In addition, we also demonstrate the implementation of fluidic matrix circuit for controlling a haptic vest, consisting of inflatable airbags that provide force feedback to the user when the bag is inflated. The pouch attached to the haptic vest was rapidly deflated to give a sensation of being hit by an object, and the deflation of pouch was accelerated by generating vacuum using fluidic modules connected to the corresponding pouch.